Welcome to the actual last video where we talk about limiting and excess reagents in stoichiometry. So here's the exciting part. All the math that you're about to see is not new. Everything we are about to do, we've already done before. So you're not learning any new math, you're just learning a new way to think about it, which again is the most important part of this math. I know you know how to multiply and divide, so let's figure out what we're actually multiplying and dividing for. I got a silly example here for you to tell you about limiting and excess reagents. And when I tell you at the beginning of the stoichiometry unit, you have done this kind of math your entire life. You already know conceptually what you are solving for. It's just when we start using chemistry things that you start to panic a little bit. Well, here we go. I have a silly recipe for pancakes. In your pantry, you have 10 cups of flour, an infinite amount of water, 12 eggs, 4 cups of sugar, and 2 cups of milk. Your recipe says you need 3 cups of flour, 1 egg, 1 cup of sugar, and 1 cup of milk to make 8 pancakes. Don't actually try this recipe, it would be terrible. Here's the deal. How many pancakes can you make? You know what you have available to you, and you know what your recipe is. So how many pancakes can you make? Well, if I were to use as much of this stuff as I could, milk is going to run out first, right? By the time I do this recipe twice, I'm going to run out of milk, right? The first time I do it, I'm going to use up 3 cups of flour, leaving me with 7. I'm going to use an egg, which is going to leave me with 11 eggs. I'm going to use up 1 cup of sugar, leaving me with 3. And I'm going to use 1 cup of milk, leaving me with 1. If I do it again, I end up with 0 cups of milk. And after you run out of milk, then the recipe is over. So the best I could do is 16 pancakes, 2 batches, right? Now, in this silly scenario, milk is what we call the limiting reagent, which is exactly what it sounds like. It is one of our reactants that will run out first. Everything else is what we call an excess reagent. So these are in excess. They will not run out. We will have leftover flour, water, eggs, sugar after we are done using up all the milk that we have, which is limiting the reaction. Limiting reagent, sometimes called the reactant. Reagent, reactant are pretty much synonyms. So when stoichiometry, it makes sense for us. Now, we're not talking about pancakes here. We're talking about chemical reactions. A limiting reactant or reagent is the thing that's going to run out first. And that will dictate what we can theoretically make. In a perfect world, if we did our very best with this reaction, and by the time we run out of our stuff, what could we make? Right? What's the best we could do? And we can do math to figure this out. Here we go. First thing we need to do here is balance this chemical equation. Unlike all the other equations in this notes packet, this one is not balanced. So we got to get it balanced. Let's see here. Well, hydrogen looks balanced. Carbon is not. Oh, but oxygen's going to be tricky. So I'll tell you what, we're going to put a 2 here. Okay? Because then that's going to give us 2 and 2 oxygens for a total of 4. But we'll get to that later. I'm going to put a 2 here to balance out hydrogens, which means I'm going to put a 4 here to balance out carbon dioxide. And then if I have 4 times 2 is 8, plus 2 is 10, I'm going to need a 5 right here to give me 10 oxygens. So there we go. 2542. Now let's do some stoichiometry. Okay, the theoretical yield tells us the maximum amount of product we can make based on the amounts of reactant we are given. So here we go. We start with 20 grams of ethine and 40 grams of oxygen. Who's limiting the reaction? Well, let's find out. And I got some news for you. There are 13 different ways that you can actually calculate this. Maybe not exactly 13, but there are so many ways that you can mathematically prove your answer. And it's up to you how you want to do it, just as long as you're doing the math correctly. I'm going to show you a few ways here. So if we completely reacted 20 grams of ethine we can pick one of these two products to analyze. Now, what I'm saying is pick one of them to analyze. If we react 20 grams of ethyne, how much CO2 did we make? If we completely react 40 grams of oxygen, how much CO2 could we make? We have to analyze the same product here in order for us to make sense of who is actually going to run out first. So let's just do the math, solve for CO2, and then we'll analyze those answers together. Here we go. We start with what we know. 20 grams of ethyne, C2H2. And we then solve for moles of C2H2. Then we solve for moles of CO2. You could do this for H2O if you wanted to, but you'd have to do H2O for both calculations. And then we solve for grams of CO2. Actually, we technically don't even need to go all the way to grams, but it's good practice. I'll show you why in a moment. So, grams of ethyne, CH2, C2H2, moles of ethyne, C2H2, and moles of CO2 as I follow my units all the way. I'm going to go quick here. 1 mole of C2H2, well, carbon's atomic mass is 12.01 times 2 plus 1.01 times 2 gives me 26.04 grams per mole. In this balanced chemical equation, for every 4 moles of CO2 that we produce, we must use 2 moles of ethyne. And for every 1 mole of CO2, the molar mass is 44.01 grams per mole. When I solve for this, I will do 20 times 1 times 4 times 44.01. That gives me 3,520.8. Wow, big number. Divided by 26.04 divided by 2, and there's my answer. 67.6, oh dear, 67.6 grams of CO2. We're going to put a pin in this for now and come back to this answer in just a moment. Let's do this calculation. If we completely use 40 grams of oxygen, how much of our product could we make? Let's see here. Well, I'm going to convert to moles of oxygen, and then I'm going to convert to moles of CO2. Again, I have to convert moles of CO2 so we can actually compare our answers, and I'm going to convert to grams of CO2. Following my units, grams, moles of O2, and moles of CO2. Good. For every 1 mole of oxygen, there are 32 grams of oxygen, because 16 times 2. In our balanced chemical equation, for every 4 moles of CO2 we produce, we must use 5 moles of oxygen, and 44.01 is our molar mass, grams per mole. Great. 40 times 4 times 44.01 equals, divided by 32 divided by 5. The answer here, 44.01 grams of CO2 are produced. Magically enough, that is actually the answer. I'm not fooling with you. 44.01 is our answer. But what does it mean? If I were to completely use 20 grams of ethyne, this is the best I could do. 67.6 grams is the theoretical maximum that I could make of CO2 if I used all of that. If we completely reacted 40 grams of oxygen, that's the best I could do, 44.01 grams. Which of these two reactants then limits the reaction? It's oxygen. Oxygen will limit the reaction, 40 grams of oxygen will limit the reaction because it can't make as much as the ethyne can. Meaning, by the time we've actually produced this much CO2, we ran out of oxygen. It's over. We can't continue making more CO2 because there's no oxygen to make that happen. The reaction is done. So, that's one way that you could solve to prove that oxygen limits the reaction. I'm going to show you a different way here and now. Let's imagine that if I take 40 grams of oxygen and I ask, well, how much ethyne would that cost, right? So I'm going to go from grams to moles, moles of oxygen to moles of ethyne, C2H2, and then I'm going to solve for grams of ethyne, C2H2. Following my units, grams of O2, moles of O2, and then moles of C2H2. For every 1 mole of oxygen, there are 32 grams of oxygen. And in our balanced chemical equation here, it says for every 2 moles of ethyne, we use 5 moles of oxygen. So that's 2 and 5. And then 26.04 grams of ethyne per mole. When I plug in these numbers, 40 times 2 times 26.04 divided by 32 divided by 5. My answer ends up being 13.02 grams of ethyne. What does this mean? If I completely use all 40 grams of oxygen, I will also need to use 13 grams of ethyne. So by the time that this is done, that's all the ethyne that I will have used. But in the calculation, we have 20 grams. So this is one way that you could solve for a limiting reagent in one shot. Compare the two reactants. Pick one of them. Start with the 40 grams of oxygen and say, well, if I use all of that, how much of the other thing am I going to need to use? And if it's, in this case, I'm not using all of my ethyne, well then, oxygen must be limiting the reaction. Just to prove it, I'm going to go the other way. Starting with the 20 grams of ethyne that we know, C2H2 over 1, I can convert to grams of oxygen to prove the same exact thing. It's just different math. Or same math, different objective. Okay, grams of C2H2, moles of C2H2, and moles of O2. So 1 mole, 1 mole. In my coefficients of the equation, 5 moles of oxygen for every 2 moles of ethyne, and then 26.04 grams of ethyne, and 32 grams of oxygen. 20 times 5 times 32 divided by 26.04 divided by 2 gives me 61.44 grams of oxygen. What does this calculation say? If I use all of this, I will also need to use this much oxygen. Do we have 61 grams of oxygen? No, we only have 40. So this can't happen. Sorry, it can't happen. This, on the other hand, can happen. Yay! We're going to run out of oxygen. No, but that's okay because that's how chemical reactions work. Eventually, we run out of stuff. Woo woo. Unless the reactant in question is listed as being in excess. Right. Now, going back to this point here, we will eventually need to solve for the theoretical yield of our products because that will help us determine whether or not we have created close to the theoretical yield or not. It's going to help us determine what our percent yield is. So let's just finish out these guided notes. Between these calculations, whichever reactant made less would be the limiting reactant. For the same reason we saw in the pancake examples, for the same reason we saw in all those extra calculations, oxygen is simply going to run out first. So we know the theoretical yield of CO2. This is the best we could theoretically do. By the time we run out of oxygen, this is the theoretical maximum that we could achieve. We can also now figure out what the theoretical maximum of water would be. So if I start with 44.01 grams of CO2, which is our theoretical yield, I can go to moles of CO2, and then I can go to moles of H2O, and then I can convert to grams of H2O. Going to put grams of CO2 in the denominator. Same with this, moles of CO2 and moles of H2O. Here we go. For every 1 mole of CO2, 44.01 grams. In this balanced chemical equation, for every 2 moles of H2O, I'm going to use 4 moles of CO2, or excuse me, also produce 4 moles of CO2. And if I'm going to 18.02, 1 mole. Great. Here we go, 44.01. Excuse me, let me try that again. 44.01 times 2 times 18.02. 1 second. Divided by 44.01 divided by 4, 9.01 grams of H2O. If this is what I can theoretically produce of CO2, then this is what I can theoretically produce of H2O. All that math is the same. It's just how you read it that will change. Now, I want to give you a little example here, talking about percent yield. So, in this example, we know that theoretical yields we've got CO2 is 44.01 grams and H2O is 9.01. Yep, 9.01 grams. So in this silly example here, let's imagine I did that reaction and I actually produced, my actual yield was 40 grams of CO2. What was my percent yield? Well, think about it. All of you, whenever you get a test grade back, immediately ask what the percentage was. Well, let's imagine that this test was worth 44 points, or 44.01 points. In this case, it's grams of CO2. And you actually got 40 grams of CO2. So you got a 40 out of 44.01, divide those numbers, multiply by 100, and baby, you got the percent yield. 40 divided by 44.01, bang! The answer is, well, times 100 then, 90.9%. Woo! How neat is that? Very easy. You can calculate the theoretical yield. I will always have to tell you the actual yield, or you could measure it yourself in a lab. So I either have to tell you or you have to measure it one way or another. That's how you get the actual yield. So you can calculate this. You have to be told or actually find this in lab. But calculating the percent yield is actually that simple. Actual over theoretical times 100 equals your percent yield. Okay, so I hope you've enjoyed all of this stoichiometry video, and if you have any questions or comments or concerns, please let me know, and I'd be happy to help. And there's a little portrait of me. Have a great day, and I'll see you on the next one. Woo!